Cement looks like plain gray powder, yet it becomes the glue that holds modern cities together.
Today we follow the entire path, from quarried rock to finished cement, step by step. But behind every bag of cement is a high-temperature factory and a complicated chemistry story. We will trace the main chain: raw mix, kiln, clinker, grinding, additives, storage, and shipping. Then we tackle the hardest question: why cement is linked to CO₂ and what can realistically reduce it. This is a modern dry process plant, built to move mountains of material with steady control. Every stage is designed for one goal: turn limestone into clinker minerals that react properly with water. Quality is monitored constantly, because tiny chemical shifts can change setting time and strength. In the end, cement must be consistent, dry, and fine enough to perform predictably at the job site.
Let's begin where it starts: the quarry, and the raw materials that set the chemistry for everything after.
First, a simple distinction. Cement is the binder powder, while concrete is cement mixed with water, sand, and gravel. Cement reacts with water to form a hardened matrix that locks aggregates into a strong, stone-like composite. That is why a small percentage of cement controls the performance of a much larger mass of concrete. Because cement is reactive, it must stay dry from the moment it leaves the mill until it meets water on site. Fineness controls reaction speed, early strength, and heat release, so mills and separators tune it carefully. From here, operators keep chemistry, temperatures, and airflow stable, because cement is a controlled industrial chemistry process. Most modern cement is mainly clinker, ground very fine, plus gypsum, and sometimes additional mineral components. So the real origin of cement is not a bag, but a rock face, and a recipe hidden inside the limestone. Cement begins in the quarry, where limestone provides calcium carbonate, the main source of lime for clinker. Not all limestone is the same, so plants map the deposit and blend zones to keep chemistry consistent. Holes are drilled for blasting, breaking massive rock into manageable fragments for loading and crushing. A controlled blast fractures the bench, creating a pile of broken limestone that excavators can quickly load. Huge loaders and excavators move hundreds of tons per hour, feeding the plant with steady raw material. The quarry is a logistics system as much as a mine, designed to deliver a controlled flow of stone. Besides limestone, cement needs silica and alumina, often supplied by clay or shale from nearby pits. Keeping materials separated early allows precise blending later, so the kiln receives the right chemical balance. Sampling begins at the quarry and continues throughout the plant, because chemistry control starts at the source. Lab preparation reduces a large rock to a representative powder, suitable for fast chemical analysis. X-ray fluorescence is commonly used to measure oxides like CaO, CO₂, alloc, and FeOc in minutes. When the raw materials vary, the plant responds by adjusting blend ratios to keep the kiln feed stable.
Modern quarries also manage dust and land restoration, because cement plants often operate for decades in one location.
Dust suppression protects workers and equipment, and it reduces material loss in windy, dry conditions. Cement demand is continuous, so many plants operate day and night to keep the kiln running steadily. Before reaching limestone, overburden may be removed, and bench stability is monitored for safety. Field checks can guide short-term decisions, but the lab remains the final authority for raw mix targets. From the quarry, material heads directly to crushing, where it is reduced so the rest of the plant can process it efficiently. Even internal material movement is tracked, because mass balance and inventory matter for stable production. Stockpiling in layers is the first step of pre-blending, smoothing out natural variability from the quarry. Reclaiming from the pile averages layers together, creating a more uniform feed before fine grinding.
Moisture matters because wet material consumes extra energy in drying, so plants manage storage and drainage carefully.
Corrective materials are stored separately, allowing operators to fine-tune silica, alumina, and iron in the raw mix. At this point, the plant has one job: make the feed consistent in size and chemistry before raw milling.
Safety and environmental controls are built into modern quarry operations because production cannot compromise people or communities.
Small corrective feeds can adjust iron or silica, letting the plant hit targets even when the quarry chemistry shifts. With raw materials secured, we move into the plant, where crushing and blending prepare the feed for the kiln.
Everything downstream depends on this steady supply, so quarry control is the first link in cement quality.
The first plant step is crushing, reducing big quarry rock so it can be handled, conveyed, and ground efficiently. Primary crushers break stone quickly, prioritizing throughput and reliability over fine particle size.
Screening and secondary crushing create a more uniform size, which stabilizes raw milling and reduces energy use.
Enclosed conveyors and dust collection keep material contained and protect equipment from abrasive cement dust.
Accurate weighing is essential because the raw mix recipe is controlled by mass, not by volume.
After crushing, the plant blends material in layers so natural quarry variation is averaged before fine grinding. The stacker and reclaimer work together like a mixing system, producing a consistent feed for the next stage. Transfer points are major dust sources, so plants use sealed chutes and suction to keep powder inside the system. Now the plant starts precise proportioning. Limestone, clay, and small correctives are combined into one controlled stream. Before the kiln, dry process plants rely on homogenization silos to smooth chemistry fluctuations even further. Aeration keeps fine raw meal moving and mixed, preventing dead zones and ensuring a uniform kiln feed. Continuous sampling checks that the blend matches target chemistry, so the kiln receives predictable material. Key checks include carbonate content and moisture, because they affect fuel demand and calcination behavior. Baghouses capture fine particles and return them to the process, reducing emissions and improving material efficiency.
Because cement runs continuously, routine maintenance prevents small failures from stopping the entire kiln line.
Magnets and detectors remove stray metal, preventing damage to high-energy grinding equipment. With crushing and blending complete, the plant is ready to grind rock into fine raw meal for the kiln. Modern plants integrate heat and material flows, using waste heat from the kiln to dry and grind the raw mix. Raw milling turns crushed rock into raw meal, a fine powder that can react uniformly inside the kiln system.
Grinding reduces particle size and exposes fresh surfaces, making later calcination and clinker formation more efficient.
In the dry process, kiln exhaust heat is reused to dry the raw materials as they are ground. Some plants use ball mills, but the goal remains the same: produce consistent raw meal with controlled fineness. The separator classifies particles, sending fine material forward and returning coarse material for more grinding. This closed loop stabilizes quality because the system self-corrects until the product meets the target size. Operators monitor vibration and power draw because grinding equipment must stay stable under heavy mechanical loads. Hydraulic pressure maintains roller force, balancing efficient grinding with wear control on abrasive minerals. Raw meal is sampled frequently because the kiln reacts differently to small changes in carbonate and silica balance. Fineness is controlled to ensure predictable heat transfer and reaction rates through the preheater and kiln. Fine dust is captured and recycled, protecting air quality and keeping valuable material inside production.
Key targets include lime saturation and silica balance because they determine how easily clinker minerals form in the kiln.
Once ground, raw meal moves by air slides and pneumatic systems, staying enclosed to avoid moisture and dust loss.
Homogenization silos reduce chemistry swings, creating a steady kiln feed that supports stable burning conditions.
Air slides move powder efficiently with minimal mechanical parts, reducing wear and keeping the material dry. Gas temperature is managed to protect filters and maintain drying efficiency, especially when raw materials are wet. Wear parts are replaced on schedule because grinding surfaces erode under constant contact with abrasive rock. Condition monitoring catches overheating or misalignment early, preventing unplanned shutdowns on critical equipment. Even after pre-blending, final proportioning continues at the mill inlet to keep the raw meal chemistry on target.
Plants balance gas flows carefully because the raw mill and kiln share heat, and changes in one affect the other.
Cyclones separate solids from gas efficiently, keeping particles moving forward while returning clean gas to the fan system.
When filtration works correctly, visible dust is minimized, and collected material is recycled instead of wasted. Now the plant has a stable raw meal, ready to enter the preheater tower, where temperature rises rapidly.
The preheater is essentially a vertical heat exchanger, designed to extract maximum value from kiln exhaust gas. As raw meal meets rising hot gas, it heats in seconds, beginning the thermal journey toward calcination.
Heat management is critical, so refractory and insulation protect steel structures while keeping energy inside the process.
Large fans drive the entire gas flow through cyclones, mills, and filters, making airflow control a core skill in cement making. Next, the calciner begins the key chemical break, turning limestone into lime and releasing the first major CO₂. The preheater raises raw meal temperature rapidly by exchanging heat with hot exhaust gas leaving the kiln.
Cyclones separate solids from gas in seconds, letting meal fall downward while gas continues upward through the tower.
Each stage lifts temperature further, so less fuel is needed later, and the kiln becomes more energy efficient.
Draft control keeps the entire system stable, preventing backflow, dust buildup, and flame instability downstream. Operators watch temperature and pressure closely, because airflow drives heat transfer and moves material through the tower. Gas composition is monitored for oxygen, carbon monoxide, and other indicators of efficient combustion and safe operation. Staged air and fuel help control nitrogen oxides, while still delivering enough heat to finish calcination efficiently. In the calciner, additional fuel is burned to raise temperature and complete most of the limestone breakdown.
Hot air recovered from the clinker cooler supplies oxygen and heat to the calciner, improving overall efficiency. Plants may burn coal, petcoke, or alternative fuels, but combustion must be stable to protect clinker quality.
At roughly 600 to 900 degrees Celsius, calcination accelerates and CO₂ begins releasing rapidly.
Chemically, calcium carbonate splits into lime and carbon dioxide, a reaction built into the raw material itself.
This is why cement emits CO₂ even before we consider fuel. The rock releases CO₂ when it becomes lime. Maintaining the right oxygen level prevents carbon monoxide spikes and keeps heat release steady for consistent calcination.
By the time meal reaches the kiln inlet, much of the carbonate is already broken down, reducing kiln load.
Dust cycles within the tower can affect chemistry, so bypasses and balancing keep salts and alkalis under control. Some plants use a bypass to remove volatile salts, protecting the kiln from buildup that can choke gas flow. Refractory protects steel from extreme heat, and its condition affects both energy use and operational reliability.
Thermal inspection helps detect heat leaks, which waste fuel and can damage structures over long operation. Stable feeding prevents surges that can destabilize the kiln flame and cause uneven clinker formation.
The induced draft fan is a hidden powerhouse. moving massive volumes of hot gas through every upstream stage.
All of this heat exchange exists to minimize fuel, because the next step demands the highest temperatures in the plant.
Now we enter the rotary kiln, where raw meal becomes clinker through intense heat and carefully controlled reactions.
The kiln rotates slowly to mix material and expose it evenly to the hottest zone, preventing localized overheating. In the burning zone, temperatures climb toward the point where clinker minerals form and nodules begin to sinter. As material heats and partially melts, it begins to fuse, creating the pebble-like clinker nodules we will cool later. Small control changes can prevent major upsets, because the kiln is a delicate balance of heat, chemistry, and time.
Ahead, we reach the hottest region, where lime reacts with silica and alumina to build the core strength minerals of cement.
Inside the rotary kiln, the material travels slowly, heating through zones until it reaches the peak burning temperature. The kiln's rotation and tilt create a controlled residence time, giving reactions minutes, not seconds, to complete. Mechanical stability matters, because misalignment can damage the shell and cause dangerous shutdowns.
The main burner delivers most of the kiln heat, and its flame shape influences clinker quality and fuel efficiency.
East Asian male operators tune the primary air and fuel. This ensures the flame remains stable, hot enough, and correctly positioned in the kiln.
Thermal scans reveal heat patterns, helping teams spot refractory wear or unexpected heat loss early. As temperature rises, particles start to sinter, and clinker nodules form through partial melting and resolidification. Near the hottest point, the mix partially melts, allowing lime and silica to react into stronger clinker minerals.
This controlled melt is essential. Too little and reactions remain incomplete. Too much and clinker can overburn.
A stable coating protects refractory and smooths temperature swings, but unstable coating can lead to quality problems.
Kiln speed changes residence time. Slower can improve reaction completion, but it can also raise heat load and risk buildup.
Upstream calcination reduces the work the kiln must do, letting the kiln focus on forming final clinker minerals. The kiln is not one uniform temperature. It has zones where different reactions dominate as the mix heats.
As reactions progress, the mineral structure changes, locking chemical energy into compounds that later react with water.
In clinker, minerals like alite and belite form, and their proportions shape early and later strength in cement. Gas flow carries heat and also moves dust, so the kiln system must balance turbulence with stable material movement. Air leaks can cool the process, waste fuel, and disturb oxygen control, so seals are monitored continuously. Some plants substitute part of fossil fuel with waste-derived fuels, but feed stability is critical for consistent burning. When chemistry drifts, operators correct it upstream, because the kiln cannot easily fix a badly balanced raw mix.
Refractory endures extreme thermal cycling, and its condition determine energy efficiency and safe operation.
Kilns prefer steady running. Frequent stops waste energy and increase wear, so plants aim for stable campaigns.
Unwanted buildups, called rings, can form if chemistry or temperature is off, restricting flow and risking shutdowns.
When conditions shift, operators respond quickly, because small instabilities can grow into major process upsets. Air registers shape mixing and combustion, influencing peak temperature, NOx formation, and clinker burnability.
The hottest gas leaving the kiln becomes the heat source for the preheater, closing the energy loop.
Once clinker is formed, it must be cooled quickly to preserve mineral structure and recover as much heat as possible.
Cooling is not just for handling. Fast cooling also helps lock in properties that affect cement strength development.
Now the process shifts from making minerals to capturing energy. The cooler turns clinker heat into usable combustion air.
Secondary air from the cooler supplies most oxygen for the flame, and its temperature strongly affects fuel demand. Clinker leaves the kiln extremely hot, so the cooler must pull heat out fast without creating excessive dust. Burner hardware is inspected often because erosion or misalignment can change the flame and destabilize the entire kiln. Shell scanners provide continuous temperature profiles, warning teams if refractory wears thin in any zone.
Feed rate affects bed depth and heat transfer. Too much feed can cool the flame zone and underburn clinker.
A consistent feed avoids temperature swings, which otherwise create variable clinker quality and increased fuel use.
Minor corrective additions can stabilize the melt phase, helping clinker form properly without excessive buildup.
Air is shared between calciner and kiln, so dampers balance oxygen and heat where it is needed most. As clinker cools, crystals solidify from the melt, and the final microstructure influences how cement hydrates later. With clinker formed, the plant's next focus is cooling, heat recovery, and preparing clinker for storage and grinding.
The grate cooler forces air through hot clinker, dropping temperature quickly while capturing heat into the airstream.
The hottest recovered air becomes secondary air for the kiln flame, reducing the amount of fuel needed for burning.
By recycling clinker heat, the plant turns waste energy into useful combustion air, improving overall thermal efficiency. A portion of hot air is diverted as tertiary air to the calciner, supporting calcination without extra fuel.
After cooling, clinker becomes solid and manageable, but it still carries enough heat to require careful handling. Cooler exhaust is filtered to control dust, and collected fines are recycled rather than released to the atmosphere. Grate speed and airflow must match production rate, keeping cooling fast without grinding clinker into dust. Operators watch bed depth and temperature patterns because uneven cooling can affect clinker quality and downstream grinding. If large clinker chunks form, a clinker breaker reduces them, so storage and grinding systems stay protected.
Cooled clinker is stored under cover to stay dry and ready for the next major stage, finish grinding. Keeping clinker dry matters because unwanted moisture can cause handling problems and reduce grinding efficiency. Now we convert clinker into cement by grinding it fine and adding small but crucial mineral components.
Finish grinding is where clinker becomes cement. The hard nodules are crushed into a fine, reactive powder. Ball mills grind by impact and abrasion, and their performance depends on charge level, liner condition, and separator efficiency.
Vertical mills can grind efficiently and dry small moisture, using air to lift fine particles toward classification. Gypsum is added in small amounts to control setting, preventing the cement from reacting too fast when water is added.
Many cements include other mineral components, lowering the clinker fraction while tailoring strength and durability.
The separator is critical. It determines fineness, which directly controls early strength and workability in concrete.
Quality control checks fineness and performance because a few microns can change hydration speed and water demand.
Grinding generates heat, so mills monitor cement temperature to avoid false set, dehydration of gypsum, or handling issues.
Some plants use grinding aids and tiny doses to reduce agglomeration and improve mill efficiency without changing cement chemistry.
Cement dust is valuable, so filtration captures it and returns it to the system, keeping emissions low and yields high.
Finished cement travels in sealed systems to keep it dry, prevent contamination, and maintain consistent bulk density.
Silos store cement safely and allow blending, giving the plant a buffer between milling and shipping.
Plants can produce multiple cement types by adjusting additive ratios and fineness while keeping the same kiln line.
Performance is confirmed by strength tests over time because customers need predictable results at 1 day, 7 days, and beyond.
Setting time is checked to ensure gypsum and clinker aluminate chemistry are balanced for practical construction use. Bagging is common for retail and small contractors, while bulk cement serves ready-mix plants and large projects.
Bulk loading must be dust-tight and accurate because customers pay by mass,
and the product must stay clean. Next, we focus on additives and blending, small ingredients that dramatically change how cement behaves in the real world. Gypsum is added mainly to control setting by regulating how fast the aluminate phase reacts with water. Without proper sulfate balance, cement can flash set, losing workability before concrete can be placed and finished. The gypsum dose is tuned carefully, because too little or too much can cause abnormal setting behavior. Beyond gypsum, many cements include additional mineral components, often called supplementary cementitious materials. Slag can improve long-term strength and durability, and it reduces the amount of clinker needed per ton of cement. Where available, fly ash can improve workability and later strength, although supply depends on local power generation. Limestone can act as a filler and react with aluminates, enabling lower clinker cements when standards allow. Calcined clays and natural pozzolans can replace part of clinker while maintaining strength, depending on local materials. Accurate dosing creates repeatable cement types, because performance depends on the clinker factor and additive proportions. It is not only chemistry. Particle size distribution matters, because different components grind differently and hydrate at different rates. Some plants intergrind additives with clinker, while others grind separately to control fineness of each component. Silo blending helps smooth short-term variations from the mill, improving consistency for customers. Additives can improve durability by reducing permeability, helping concrete resist sulfates, chlorides, and freeze-thaw damage. Different cement blends change workability and heat release, which matters for pumping, finishing, and mass concrete pours.
Lower clinker cements can reduce heat of hydration, helping large pours avoid thermal cracking.
Plants validate each cement type against standards for strength, setting time, soundness, and consistency.
Soundness checks confirm the cement will not expand unpredictably, protecting structures from long-term cracking.
In practice, additive use depends on supply chains and local standards, so plants plan blends around reliable materials.
Different products are stored separately to prevent contamination, because even small mixing can change performance. Cement is global but heavy, so logistics costs matter. Plants often serve regional markets within practical transport distance. Traceability matters, so plants retain samples and records, allowing investigation if a customer reports an issue later. Now we confront the emissions story. Cement's CO₂ comes from both fuel and chemistry, and the chemistry part is unavoidable. Once cement is in silos, the plant can ship continuously, even if the mill briefly stops for maintenance. Bulk systems keep cement dry and minimize dust, using sealed connections and filters at every transfer point.
Accurate loading protects customers and the plant, because small percentage errors become large at high throughput.
Bagged cement serves smaller users, and dust control is essential to keep the product weight accurate and the air clean. Packaging and storage must protect cement from moisture, because even brief humidity can start unwanted hydration.
Random checks confirm that packaging, mass, and product properties match the plant's specification.
Most cement is used quickly at batching plants, where precise dosing and moisture control produce consistent concrete.
Because cement is heavy and low value per kilogram, plants compete on reliability, distance, and consistent quality.
The same system that makes clinker also generates most emissions, so understanding process steps explains the CO₂ story.
To cut cement emissions, we must separate two sources, heat-related COM and chemistry-related COM from limestone breakdown.
Cement CO₂ comes from two places, burning fuel for heat and the chemical release of CO₂ when limestone becomes lime. The key reaction is simple. Calcium carbonate breaks into calcium oxide and carbon dioxide as temperature rises.
That carbon dioxide is inherent to the rock, so it appears even if the heat source becomes cleaner.
The second share is energy emissions. Fuels burn to reach kiln temperatures near the burning zone and calciner.
A common rule of thumb is that process chemistry can be around 60% of direct emissions, with fuel around 40%.
Because clinker formation causes most emissions, the clinker content of cement strongly influences the carbon footprint.
Plants measure oxygen, carbon monoxide, and dust, and they calculate CO₂ using fuel data and process models. Continuous monitoring ensures environmental compliance, while filters keep particulate emissions low despite high material throughput.
Globally, cement is responsible for a significant share of CO₂, often cited at roughly 7% of total emissions.
Chemistry emissions occur mainly during calcination, before the material even reaches the hottest burning zone.
Electricity for grinding and fans can add indirect emissions, so decarbonizing the grid also helps cement plants. Efficiency measures reduce fuel use by recovering heat, but they cannot eliminate the chemistry CO₂ released from limestone.
This is why cement is called hard to abate. The emissions are partly a chemical byproduct, not just an energy choice.
One of the most practical levers is using less clinker per ton of cement by replacing part of it with other minerals.
Another lever is cleaner heat, better combustion, different fuels, and eventually new heat sources that cut fossil CO₂.
For deep reductions, many experts see carbon capture as necessary, because it can address the chemistry CO₂ directly.
Reducing the clinker ratio is the fastest route to lower emissions, because it cuts both fuel and process CO₂ per ton.
Blended cements must still meet strength and setting requirements, so plants validate performance with standardized tests.
Where materials allow, calcined clays and limestone blends can reduce clinker while maintaining durability and workable concrete.
Switching fuels can reduce fossil carbon, but stability and emissions control must remain tight to protect clinker quality.
Biogenic fuels may lower net fossil CO₂, but plants still need precise combustion to avoid CO spikes and excess emissions.
Reducing heat loss and false air improves efficiency, cutting fuel per ton of clinker without changing product quality.
Electric efficiency matters too, because fans and mills consume significant power, and cleaner grids reduce indirect emissions.
Electrifying kiln heat is challenging at today's scale, but research continues on new high-temperature heating approaches. Hydrogen is discussed as a future fuel, but flame characteristics, cost, and supply make large-scale adoption difficult today.
Carbon capture targets the CO₂ in exhaust gas, offering a direct way to reduce emissions even when chemistry releases CO₂. Captured CO₂ must be compressed and transported for storage or use, so capture is only one part of the full system. Permanent storage aims to lock CO₂ away underground, turning a gas waste stream into a managed industrial byproduct.
Beyond factories, using cement more efficiently in concrete can cut emissions, because the cleanest cement is the cement not used.
Recycling and improved design can reduce virgin material demand, supporting a broader circular approach in construction.
In practice, deep cuts come from combining lower clinker, cleaner heat, better efficiency, and capture where required.
Cement will remain essential, but its future depends on smarter chemistry, smarter energy, and smarter use across the whole value chain.